You ever look up at a massive jumbo jet and just think to yourself, how in the world does that thing stay up there? It just seems to defy gravity. Well, it's not magic, it's all physics. And it pretty much all comes down to one brilliantly designed shape. So let's peel back the layers and find out how a wing really works. Here's how we're going to break it down. We'll start with the shape that makes it all possible. Then we'll follow the air as it flows over the wing. After that, we'll learn some of the key terminology, get a handle on the forces at play, and finally, we'll see how pilots actually use all this to control the plane. So let's kick things off with the hero of our story, that simple but elegant shape that really unlocks the secret of flight. And here it is, the aerofoil. The source material defines it perfectly, a shape that's really, really good at producing lift. If you could just slice a wing open and look at it from the side, this is the cross-section you would see. It's the fundamental building block for pretty much everything that flies. That is the million-dollar question, isn't it? How can a simple shape like this have such incredible power? Well, to figure that out, we actually have to follow the air on its journey around the wing. So, let's trace the exact path the air takes as it meets the wing, splits, and flows around this aerofoil shape. You know, what's really interesting is that the wing's influence actually starts before the air even touches it. There's this low pressure zone that forms over the top, and it reaches out ahead of the wing and literally pulls the incoming air upwards. We call this phenomenon upwash. So as that air gets to the very front of the wing, the leading edge, it hits a specific spot called the stagnation point. And right there, just for a split second, the air stops dead in its tracks. It has to make a choice, go over the top or go underneath. And this, right here, is the absolute heart of it all. The air that goes over that longer, curved top surface has to speed up to make the trip. Faster air means lower pressure. Meanwhile, the air on the flatter bottom surface moves slower, which creates higher pressure. And that pressure difference, that's the key. The stronger push from below simply overpowers the weaker pressure from above, and that creates the upward force we call lift. Okay, so now that we've seen the basic idea, it's time to learn the lingo. To really get into the physics, we need to know what to call all the different parts we're talking about. First up is the chord line. Just think of it as a reference line, like a ruler. It's a perfectly straight line drawn from the very front of the aerofoil to the very back. Pretty much everything else is measured in relation to this line. Next, we've got the mean camber line. Now this one is the actual center line of the aerofoil, curving perfectly halfway between the top and the bottom. The amount this line curves, we call that camber, and this is a huge deal for aircraft designers. A wing with a lot of camber, a big curve, is awesome at making lift at low speeds, perfect for something like a heavy cargo plane trying to take off. Now, this one is super important to get right. The angle of incidence is a fixed, built-in angle. It's literally the angle at which the wing is bolted onto the plane's body. This angle doesn't change in flight. It's set by the engineers to give the wing a little bit of an upward tilt, even when the plane itself is flying totally level. Okay, anatomy lesson complete. Now we can finally talk about the forces that these shapes create. And this brings us to what is, without a doubt, one of the most important concepts a pilot has to manage. So before we can properly define lift, we need to understand the air the wing is actually flying through. We call this the relative airflow. The easiest way to picture it is to think about sticking your hand out of a moving car window. The wind you feel is the relative airflow. It's always coming from the exact opposite direction you're traveling, and its speed matches your speed. For a plane, we also say it's the unaffected air, the air that's far enough away that the plane hasn't disturbed it yet. So once you have that idea of relative airflow in your head, the definitions for lift and drag get really simple. Lift is the force that always acts at a perfect 90-degree angle to that airflow. Always. And drag is the force that acts perfectly parallel to it, pulling backward. They're really just two different components of the same total aerodynamic force. And that brings us to the most critical, most important variable in all of flight, the angle of attack, or alpha. This is simply the angle between the wing's chord line and that oncoming relative airflow. And here's the crucial part. Unlike the fixed angle of incidence, the pilot can change this angle anytime they want. It is their #1 tool for controlling how much lift the wings are making. So let's bring it all together. We know what lift is, we know the terminology, and we know the pilot's main tool is the angle of attack. So how do they actually use this knowledge in the real world to get a plane off the ground and climbing into the sky? It really just boils down to two main things a pilot can do. First, they can go faster. More speed equals more air over the wings. Second, they can increase the angle of attack, pitching the nose up into the wind. Let's look at how each of those works.
First up, speed. This one's pretty intuitive, right? The faster the wing slices through the air, the more dramatic that pressure difference becomes between the top and the bottom. You're forcing more air over and under the wing every second, which just amplifies the whole effect and generates more lift. Simple as that.
And second, the angle of attack. By tilting the wing's front edge up, the pilot is forcing the air on top to travel an even longer, curvier path. That makes it accelerate even more, which drops the pressure up there even further. So what happens? The pressure differential gets bigger and you get more lift.
But creating all this lift is a really delicate dance. The whole system is incredibly sensitive. And a quote from our source material really drives this point home. It points out that even tiny little imperfections, things like a small dent, some dirt, or even a thin layer of frost right on that leading edge, can totally mess up the airflow and seriously reduce the wing's ability to fly. So, we've established that increasing the angle of attack is the main way to get more lift. It's how planes take off, it's how they climb. But that leads to one last really crucial question. What happens if you just keep pulling back? If you keep increasing that angle, tilting the wing further and further into the wind? Is there a limit? And what happens when you finally cross it?